Okay, so we are on page 7 of our workbooks. We are going to be on lesson 2. We're simplifying radical expressions and solving equations, and this is day 3 of notes for this particular lesson. So, for numbers 1 through 6, we are told to determine whether these are like radicals. So, if we look at number 1, anytime we're looking for like radicals, we're looking at what's underneath our radical sign. So in this case, they both have 3's. If you think about like terms, so if I had, let's say, let's just change these to x's instead. So if I had x and 5x, it's saying, okay, would those be like terms? And yes, they would. So these are also like radicals because they have the same number underneath the radical. So yes, these are like radicals. So with number 2, if you look underneath the radical sign again, you have 18. Now, we did talk about simplifying radicals, and most of the time we're going to want to look and see if they can be simplified, and 18 technically can, but since 18 is going to break down to the same thing here as it is here, it's still going to be like radicals. So we are going to say, yep, they have the same thing underneath the radical, so they are considered like radicals as well. For number 3, if you look underneath the radical here, we have a 7. That is a prime number, so that can't be broken down at all with our factor tree. So we actually are not going to be able to simplify that radical. And then with this one, we have a 5 here. That's also prime. So you can't break that down either. So if we look and say, okay, is 7 the same as 5? No, it's not. So we can say, no, these are not like radicals. Okay, moving on to number 4. The issue with number 4 is 12 can be broken down. So let's go ahead and let's do our factor tree because we want to simplify these first. We want to figure out, since they aren't just automatically the same, 12 is not the same as 27. It looks like they're not the same. It looks like they're not going to be like radicals, but let's go ahead and break down and see. If we break 12 down, we can break that down to 4 and 3. If you broke it down to 6 and 2, that's fine also. It's still going to end up giving you the same answer. So I broke down 12 to 4 and 3 though. 3 is prime, so I'm just going to circle that. 4 is not, so let's break that down to 2 and 2. Okay, and let's go ahead and circle those. Now, excuse me, with lesson, let's see, looking back at my notes, we simplified radicals in lesson 2, day 1. So if we're looking at this, we should already know how to break down that 12 and get it down to everything we need. And if you look, we have a pair of 2's, which is what we're looking for, is pairs. So I'm going to take one of those from my pair, and I'm going to say, okay, that goes outside the radical. And then I have a 3, a loner 3 that's going to stay inside the radical. Okay, I always explain to my students whenever we're actually in class and in person, I always say, okay, well, the pairs go out. Pairs always like to go out. If you're a couple, you like to go out. If you are more of a loner and you don't like to do too much, you just rather would stay in, you stay in underneath the radical. So if that helps you kind of remember what stays in the radical and what goes out. So then I say, okay, well, 5 times 2 is 10, and I have 10 root 3. So let's go ahead and let's break down that 27. I'm going to go ahead and switch colors so it doesn't get too clustered here. So that 27 can be broken down to 9 and 3. 3 is prime. 9 is not, so we can break that down to 3 and 3. And I always just circle so that I don't lose everything. So if you look here, we have a pair of 3s right here. And we have a loner 3 right here. So I'm going to take the 2 that I have. I don't want to forget about that. And then I'm going to pull out one of my pairs. So I'm going to take that 3. And then my loner 3 here is staying inside. Doesn't like to go out, so it's going to stay inside the radical. So I can take 2 times 3 and get 6 root 3. So if I look at these now, what my original question is asking me, well, are these like radicals? So I want to look here and here, and underneath the radical, I see a 3 on both of them. So these are going to be considered like radicals. All right, let's see here. With number 5, if you automatically notice 100 is a perfect square. So we can say, well, what is the square root of 100? And that's going to be 10. So it's really just saying 5 times 10, which is 50. And here we have 2 root 50. So let's go ahead and let's break that down. I'm just going to put a 50 under here. Sorry. Wrote too big. So let's break that 50 down, and we can break that down to 25 and 2. 2 is prime, 25 is not, so that gets broken down into 5 and 5. Again, you do not have to break it down the same way I did. You could have said 5 times 10 to start out instead of 25 times 2, and that would have been fine. You still would have broken it down to get the same answer. So if we look here, we have our pair of 5s, and we have a loner 2. So I'm going to bring that 2 out here. I'm going to take one of those 5s out, and my loner 2 stays underneath the radical. So I end up with 10 root 2, and I have my 50 over here. Those are not like radicals. 50 doesn't even have a radical on it. So we're going to say no. Those are not like radicals. All right, moving on to the last one. So with number 6, if you notice, 49 is a perfect square, and the square root of 49 is going to be 7. So we have 5 times 7 is equal to 35. Okay, that's the simplified version of 5 root 49. And then we want to look at the second part. Well, the square root of 16 is actually 4. Okay, so that's another perfect square. If you don't know that and you break it down, you will still get the fact that it's a perfect square. So I'm going to say 2 times 4 then is going to be 8. So I get 8 and 35. And I kind of look at this actually 2 ways. For one, it doesn't have a radical. So a lot of you are probably going to be like, nope, it's not a like radical. But technically, the square root of 1 is 1. And if I take 1 times any of these, it's still going to give me the same answer. So if I had 35 root 1 and I had 8 root 1, technically they still have the same number underneath here. So they do have like radicals. So some people might say yes. I really don't know which one I would prefer. I would probably look at that at first and say, well, 35 and 8, they don't even have radicals, so they're not like. It's kind of a teacher preference, I would think. All right. So moving on. Let's go down to number 7. We're simplifying each radical expression, and we want absolutely no decimals. So we are adding and subtracting our radicals. Now, the only time we can add and subtract radicals together are if they have like radicals. So that's why we did that first part up here. That was like 1 through 6. That is why we went ahead and tried to figure out which ones were like. So if we look at number 7, 7 and 8 are probably the simplest version of this type of question that we would get. So if you look at 7, we have root 3 and root 3, which means those are like radicals. The only thing you have to do, you do not add what's inside the radical. You keep the root 3, and you add what's in front of the radical. So we have a 4, and we actually have something in front of that first root 3. We have a 1, because 1 times anything is just itself. So if I take 1 plus 4, I end up with 5 root 3s. So 5 root 3 would be my final answer. Okay, so then let's move on to number 8, because it's very similar. So I have root 5 and root 5, which means that those are like radicals. So what I need to do is I need to add or subtract what's in front of them. So I have negative 2 minus 4. So if I take negative 2 minus 4, I get negative 6 root 5. The root always stays the same. So then for number 9, it looks like they're not like radicals. So it looks like we really can't do anything. But we can actually break down 12. We're going to simplify that radical. So if I break down 12, I can break it down to 4 and 3. Again, if you break down to 6 and 2, that's perfectly fine. You're still going to get the same answer. But 3 is prime, and 4 can get broken down to 2 and 2. So if I look at this, I already have the 2 out front. I have a pair of 2s, so I'm going to bring one of those out because couples like to go out. And then I am going to leave the loner that I have here. He's going to stay inside. Okay, so that loner 3 is staying inside. So I end up with 2 times 2 is 4 root 3. That's my simplified version of 2 root 12. And then I still have plus another 4 root 3. So basically I'm asking, well, how many root 3s do I have? So I have these, they are like, I'm going to say 4 plus 4 gives me 8 of those root 3s. Okay, so moving on. Sorry, my chair's squeaky. I'm trying to get comfortable. So with 18 and 50, neither of those are like, or I'm sorry, they're not like together. But also neither one of them are fully simplified. So let's go ahead and let's break down this 18. I'm going to break it down to 6 and 3. 3 is prime, but 6 is not, and that breaks down to 3 and 2. And those are both prime. So if I look, I still have that negative 2 out front. I'm going to bring that down. I have a pair of 3s. They're not right next to each other, which is perfectly fine, but I do have this pair of 3s right here. So I'm going to go ahead and bring one of those out. And then my loner 2 here is going to stay inside. So if I take the negative 2 times the 3, I get negative 6 root 2. Okay, now let's break down the 50. So if I break down 50, I get 25 times 2. 2 is prime. 25 breaks down to 5 and 5. And then I can say, okay, well, I have that 4 out front. I have a pair of 5, so I'm going to bring one of those out. And I have a loner 2 that's going to stay underneath the radical. So I have 4 times 5 is 20. And then the root 2 stays underneath the radical. So I end up having negative 6 root 2 plus 20 root 2.
Needs to be moved for delivery. There is a car sitting in the dock area. Please remove it so that we can get a delivery truck in. Thank you.
See, it's like you're back at school with announcements. All right, so I have -6 plus 20 is going to give me 14, and then my root 2 stays the same. And I can only add and subtract those because of the fact that we have, like radicals. All right, moving on. So for number 11, if you look at this one looks like, oh man, we have 3 radicals now that we have to simplify. Looks like a lot of work, but it's actually not. Because 6 root 7, if you look at the 7, that's prime. It's already simplified. 4 root 3 is already simplified. But 28 is not. So let's go ahead and let's break that down because that is not a prime number. So I'm going to say 7 times 4. 7 is prime, and then I can break down 4 to 2 and 2. So if I look at this, I'm going to go ahead and bring down the 6 root 7 and the 4 root 3. And now I have minus, well, there's really nothing in front besides that 1. So really, I'm just going to bring one of my 2s, one of my pairs. So I'm going to take that 2 out, and I'm going to have the 7 left underneath the radical. So if I look at this expression now, 7 and 3 are not like, so I cannot combine those together. But I have a root 7 here, and I have a root 7 here. So I can combine the 6 root 7 and the -2 root 7. So I'm going to say 6 minus 2 is 4 root 7. And I still have to go ahead and include that 4 root 3. So I'm going to say plus 4 root 3. This would actually be my final answer. I can't take that any further. That is simplified as far as it can go. All right. Now, with number 12, I look at this and I see that we can get rid of some stuff. So I have a 5 root 3 here, and I have a -5 root 3 here. So if I were to say, well, what's 2 minus 2? It's going to give me 0. I have something, and I'm getting rid of it. So I'm just going to go ahead and cancel those out. So I'm left with 2 root 20. Now, do not leave it as 2 root 20 because that is not simplified as far as it can go. We want to go ahead and break 20 down. So I'm going to just say 2 times 10. 2 is prime. Let's break down 10 to 2 times 5. Okay. And so if we look at this, I have a pair of 2s. So I'm going to bring one of those 2s out, but I already have a 2 out front also. So I bring one of my 2s out, and then my loner 5 stays underneath the radical, so I end up with, that is not right. Don't know why I wrote that. 2 times 2, which gives me 4 root 5. And that's going to be my final answer. All right. 13. I really hope that you guys already kind of see that 49 is a perfect square and so is 25. If you can notice these things right off the bat, it's going to make it a lot easier to deal with. So right now, I'm not going to do anything with the 5 root 25. I'm just going to rewrite that. I'm sorry, 5 root 24. But with these other ones, I have 3 times the square root of 49. And the square root of 49 is a perfect square. So that's going to be 7. So I'm going to say plus 3 times 7 minus, and then I have 5. Well, 25 is a perfect square also. The square root of 25 is 5. Okay, so I end up with this expression. So I'm going to say, well, 5 root 24 plus, I have 21 minus 25. So again, these are my constants. I can go ahead and I can add those together. So I have 5 root 24. 21 minus 25 is going to give me -4. And a lot of you might want to stop here, but we're not quite done because 24 is not simplified. That is not a prime number, so we have to break that down. So we're going to break that down to 6 times 4, and then 3 times 2, which makes those both prime, and then 2 times 2. Okay, so I already have a 5 outside. I have a pair of 2s right here. So I'm going to bring one of those pairs out. And then I have a loner 3 and I have a loner 2. So both of those stay underneath the radical and get multiplied together. Okay, so I end up with 5 times 2 gives me 10. 3 times 2 gives me 6. So 10 root 6. And don't forget about that negative 4 you had out here. So minus 4. All right, so then we have number 14. It says find the perimeter and area of a square that has a side length of 10 root 2. So it's only giving us one side length, but we should know from probably middle school and elementary school that a square, and don't make fun of my square. Let's see, am I able to, nope. I was going to try to make it pretty, but it's not going to work. Okay, we should know that a square, all the sides are the same. So if I know one of my sides is 10 root 2, that means every single side of my square is 10 root 2. Now, the other thing that we should know how to find is perimeter and area. So perimeter is the distance around. So if I wanted to go around the perimeter of a building, that means I'm walking around the entire building. Like if somebody were to say like check your perimeter, that means that they're checking around to make sure that there's nothing around. Okay, so I'm gonna just add up all of my sides. So I'm taking 10 root 2 plus 10 root 2 plus 10 root 2 plus 10 root 2. Okay, and if I do that, here, let me try to finish that out there. Oh my goodness, that made it look 10 times worse. Okay, so if I try to finish that out, I can see, okay, I have root 2, root 2, root 2, and root 2. Those are all like. They all are like radicals. So I'm just going to add up my fronts. So I'm going to say 10 plus 10 plus 10 plus 10 gives me 40. My radical stays the same, root 2. And since we are talking about a distance, with perimeter, we just use like centimeters or inches or feet or something like that. And since we're not given that, I'm just going to say units. And so I'm just going to put a U for units, whatever our unit is. Now with area, we take our side and square it, or for the area of a square, we can take length times width or side times side. Okay, there's a lot of different ways to write it. So I'm just going to take one of my sides times one of my sides. So I'm going to say, well, 10 root 2 times 10 root 2. So I don't know. Yeah, it looks like you did this yesterday. So day 2 of our notes. So what we're doing is we're going to take our outsides and take them and multiply them together. So 10 times 10 gives me 100. And then root 2 times root 2. Anytime you multiply the two things together that are the exact same, it just gives you the 2 underneath the radical. You could, if you don't know how to do that for sure, you can say, well, 2 times 2 is going to be 4. So it's 100 root 4. And the square root of 4 is 2 because it is a perfect square. So that's 100 times 2. So we end up with 200 either way. So 200, and with area, I hope you guys remember whenever we're talking about units, we're doing units squared with area. Anytime we talk about perimeter, it's just the units. Anytime we talk about area, it's units squared. And anytime we're going to be talking about volume, it's going to end up being units cubed. So units to the 3rd power. Okay, moving on. Let's change colors up again. I'm feeling colorful. Okay, number 15 and 16, it says solve each equation below by clearing out the fractions. So anytime we're looking at problems like this, you guys see fractions and you're like, yep, nope, I don't want to do this. So we want to clear those fractions out. So the thing that we have to do is we have to look at our denominators. We have a 3, a 2, and a 6. And we want to come up with the least common denominator. Okay? So, or at least common multiple, really. So we're going to look and we're going to say, okay, 3 and 2 can't be our small number that we're going to multiply by. It has to be at least as big as the biggest number. So we're looking at our 6 here. Well, 3 and 2 both go into 6. So we can multiply this entire thing by our 6. Okay, so if we do that, we can take 6 times 14 over 3. And if you do that, I did the work, I just don't know what it is again. Okay, if you take 14 over 3 times 6, you end up with 28. Then we can take and say, well, that's equal to 1/2 times 6 is 3a. And then 11 over 6a times 6 is just going to give us 11a. So I end up with 28 equals 14a if I add these two together. Okay, then I can go ahead and solve this like a normal equation and divide by 14. And I get 2 is equal to a. So we solved our equation by getting rid of that fraction. All right. Then if we look at number 16, I have -5/2 as a fraction. I have 1/3 as a fraction, -7/8. And then I have -1/3. Or I'm sorry, 3 and 1/3. I don't want that, okay? I want to get rid of this, and if you guys remember correctly on how to get rid of that 3 out front, make it an improper fraction, I'm just going to rewrite here. Hold on while I'm talking. Okay, how to get rid of that, we're going to take the 3 times the 3, which gives me 9, and then we're going to add the top, our numerator, and we get 9 plus 1 is 10, over, and we keep our denominator of 3. Okay, so we've turned that into an improper fraction, and that's how we want it. I don't really like how we had that written. Okay, so then I need to, again, look at my denominators. I have a 2, a 3, a 3, and an 18. Least common multiple. So I'm going to look and I'm going to say, okay, well, 18 is going to be my smallest thing that everything can go into. Okay, 2 goes into 18, 3 goes into 18. So I'm going to multiply this entire thing by 18. Okay, 18 times -5/2 is actually -45x. 1/3 times 18 is going to give us 6x. And that's going to be equal to, if we take -7 over 18 times 18, that's going to give us -7. And then -10/3 x times 18 gives us -60x. Okay, this looks like an equation that we would much rather work with than all of those fractions. So I'm just going to say, well, -45x plus 6x, that's going to give me -39x. And that's equal to -7 minus 60x. I'm going to go ahead and move that 60x over, so I'm going to add it over to the other side. And I get 21x equals -7. And then I am going to divide by 21. And that actually gives me a fraction, so it gives me negative 7 over 21, but that negative 7 over 21 is not simplified. It's not a simplest version, so I'm going to go ahead and divide both the top and the bottom. I don't know why I said 3. Losing my mind. Okay, divide both the top and the bottom by 7. That's the biggest thing that can go into both of them. So that's actually going to end up giving me x equals negative 1/3. Okay, we only have a few left. Sorry, writing something down real quick so I don't forget. All right, let's move on to the last 4. So, we are going to solve each of these equations, and it says, if necessary, leave in simplest radical form. That is going to be necessary on a couple of them. And then it says, also determine if the given equation is linear or quadratic. So, probably the first thing we need to talk about is what is linear and quadratic. We should have talked about this last year in either Algebra 1 or Algebra 1B, either one. Linear is whenever you just have an x term. So it's x to the first power. The first power is the highest power. Okay? Quadratic is whenever your highest power is of 2. So your highest exponent, sorry, I lost my words. The highest exponent is 2. So I'm just going to put a 1 and a 2 so that we remember that. So with number 17, whenever you have 2 fractions, I am like losing my mind today. Whenever you have 2 fractions like this, what you're going to do is you're going to cross multiply. So we're going to take this 4 times 3. Now, if you look, we have this negative sign out front. You can either give that to the 4 or the 3. I usually give it to the first one so I don't forget about it. So I say, okay, well, negative 4, and then that negative's gone. Negative 4 times 3 is going to give me negative 12. And then I'm going to cross multiply here. Now, I don't just take 7 times n. I have to take 7 times the entire n plus 1. So I'm going to go ahead and put that in parentheses. I'm breaking stuff now. Okay, so we have negative 12 equals, and this we're going to have to distribute with. Okay, so I'm going to take 7 times n, and I get 7n. And then 7 times 1 gives me 7. And I'm going to go ahead and subtract my 7 and solve it like a normal equation. So I get negative 19 equals 7n. And I'm going to divide by 7. So I get negative 19 over 7 equals n. Now, if you look at this, we can't simplify that any further. That is our reduced fraction. That's negative 19 over 7. Now, we did forget about one part of our directions, though. It says also determine if the given equation is linear or quadratic. If you look here, we don't see an n. Our n here does not go to the second power. It's only to the first power, technically. Okay, so that's going to be a linear equation. Okay, we're going to do the same thing with 18. Since we have 2 fractions, 1 on each side, we're going to go ahead and cross multiply. So we're going to take 4 times the quantity n plus 10. We cannot just say 4 times n and then have the plus 10. So we are going to take 4 times the entire n plus 10. And we're going to take 7 times the entire n minus 1. Okay, again, like we did over here, we are going to distribute. Okay, so 4 times n gives me 4n. 4 times 10 gives me 40. And then that's going to be equal to 7 times n, which is 7n. And 7 times negative 1, which is negative 7. This, again, looks so much easier to deal with. So we're just going to start solving like we know how to solve an equation. I'm going to take I'm going to subtract the 7n, which gives me negative 3n plus 40. equals, that cancels, and I get negative 7. I'm going to subtract the 40 now on both sides, which gives me negative 3n equals negative 47. And then I'm going to divide by my negative 3 to get n by itself. So I get n equals negative 47 over negative 3. Now, there is one thing that I want to point out. This is not going to be my final answer because these negatives, since I have a negative on top and bottom, if you divide two negatives, it becomes positive. So this entire answer is going to be positive instead. So it's going to be 47 over 3. With that being said, we can't forget the last part of our directions. Is it linear or quadratic? We don't have anything where it says n to the second power. So this is going to be linear because it's only n to the first power. Okay, 19. I'm about to lose my power on my pen, so I gotta hurry up here. 19, 11 times 11, I'm going to cross multiply again, is 121. Okay, x times x, we should know that is not 2x, it's x squared. Now, this looks a little bit different. This has an exponent of 2, so this one's actually going to be quadratic. We'll go ahead and answer that now. Okay, now, I need to know how to solve for a quadratic like this. So I'm going to go ahead and I'm going to take the square root to get rid of that 2. So that square root cancels out the square. They're inverse operations, so they cancel each other out. So I just get x left. And then I want to take the square root of 121. And it's actually a perfect square. It's 11. But I am forgetting one thing. Whenever you take the square root, it can always be a plus or a negative. So we always want to have that plus or minus 11, or plus or minus our answer. And that's actually going to be our final answer. Then if we look at 20, I'm going to take x times x, and that's going to give me x squared. Then I'm going to take 6 times 8, and that is going to give me 48. Okay, again, I can probably answer the fact that this is also quadratic because we have an exponent of 2. Okay, and then again, we want to do our inverse operation to get x by itself and solve for x. We're going to take the square root of that squared, x squared, and they're going to cancel each other out. Okay, so we get left with x, but since we did it to that side, we also have to take the square root of 48. And the square root of 48 breaks down. I'm going to get some extra room here. So we're going to go ahead and break that down because that is not prime. So we're going to say, let's just take 8 times 6. Okay. Then we're going to say 4 times 2. 2 is prime. 4 is not, so let's break that down further. We get 2 and 2. Then if we break down 6, we get 3 and 2. So we have to find all our pairs. We have a pair of 2's here. Okay, we also have a pair of 2's here. We have one here and one here. So I'm going to try to circle those kind of. Okay, so we have 2 pairs of 2's. So I'm going to go ahead and bring out one from this pair. And then I'm going to bring out a 2 from this pair up here. And then the other thing that we have is we have that loner 3 we don't want to forget about. We're going to leave that underneath the radical. So we end up with x equals 2 times 2 is 4 root 3. But that's only half my answer. I'm not 100% done. Okay, the reasoning is over here on number 19, we talked about the plus or minus sign. This right here. You must have that on these whenever you're taking the square roots. So our answer is going to be x equals plus or minus 4 root 3. And what that really means is x can equal 4 root 3, or it can equal -4 root 3. So you really have two answers. That's what that plus or minus is telling us. Okay. Go ahead and circle these so that we don't lose them in here. All right, and that is going to be it for day 3 of lesson 2 notes.